Good evening, everyone. I am Professor Shalini Sahay from EC Department, Sagar Institute of Research and Technology. Today, I am going to discuss about the properties of Z transform and its ROC in this lecture. Now, first we introduce and talk about the Z transform. Its theory is based same as with the Laplace transform. As all we know that Laplace transform is used to convert differential equations into the algebraic equation. Likewise, the Z transform is also a special case like Laplace transform, and it converts the difference equation into algebraic equations. We know that the convolution of the two signals results in the product of the Z transform. So Z transform is very useful in the signal processing. Now, the Z transform, it is a special case of the Laplace transform and results from applying the Laplace transform to a discrete time signal. Here, we will convert this Laplace transform into the Z transform by converting the transform to the discrete time signal. XX, this is the Laplace transform, that is S represents the S domain, where the real part, it is your sigma, and imaginary part is the j omega. Here we are integrating the continuous time signal. This is the Laplace transform. Now here we are converting the limit del t tends to 0, and this continuation sign, that is the integral sign, is now changed into the summation sign as the Z transform is used for the discrete time signal. Now let us consider this transformation maps the S plane. This is the S plane and it will be equivalent to the Z plane. So this is the S plane which is used for the continuous time signals, and here the Z transform which is used for the discrete time signals. Here we have put S is equals to j omega and Z is equals to ES, and this is the time change del t, matlab small change in the time. Now j omega axis maps the unit circle. Now as we know that the Laplace transform S is equals to sigma plus j omega, where sigma represents the real part and this is the imaginary part. So by putting the here S, we are converting this Laplace transform into the Z transform. Now if we know that continuous time system is stable as its pole lies on the left side of the half plane. So as we know that if a system is stable, then all the poles should lie on the left hand side. Now if we consider the discrete time system, now the stability condition will be if its poles are inside the unit circle. So we, in terms of the discrete time signal, we say that all poles should lie in the inside this boundary, means unit circle. The Z transform behaves much like the Laplace transform and can be applied to difference equation and to produce frequency and time domain responses. Now we'll consider ROC. ROC, which means that region of converge, and its relationship to the discrete time Fourier transform. Now we can derive the discrete time Fourier transform by setting Z is equals to R e to the power of j omega. So now we will relate that the Z transform is very much related with the discrete time Fourier transform. So in the equation, Z transform equation is x, Z is equals to summation of xn e to the power of minus j omega n. Now in this case, what we have done, that we have put the value of Z is equals to R e to the power of j omega. And by substituting, we find that the ROC is the region uh, for which this summation means Z transform value should be less than infinity. So it should consider a finite value. Now depending only on R is equals to mod of Z, just like the ROC in the S plane for the Laplace transform depends only on the real part. So for the region of converge, we have to depend only upon the real part. Now, if the unit circle is in the ROC, then discrete time Fourier transform exists. For example, if we take a signal a to the power of n un, a right-sided signal. So we know that this unit step function exists from 0 to infinity. Now, if we find the Z transform for the given signal, what we have done, xn is replaced by xz, which indicates that we are finding the Z transform. Now we put this signal in the definition of the Z transform, where the summation sign n minus infinity to plus infinity, and this is the signal, and Z to the power of minus n. Now what we have done, put the limits. So any signal which is multiplied by the unit step signal, then its limits will be changed from 0 to infinity. So we have taken the summation sign, and n from 0 to infinity, a to the power of n, un, the value of unit step function is 1. So we have taken 1 instead of un, and now this will become an infinite series. So by putting the values of n is equals to 0, the first element will be 1. Then we'll put the value of n is equals to 1. Then we'll put the value of n is equals to 2. So it will form an infinite series whose sum is represented by 1 upon 1 minus az minus 1, which indicates that ROC is an outside a circle of radius a and includes the unit circle, which means its discrete time Fourier transform exists. So there is a 0 at z is equals to 0, and we'll have a pole. So this is the pole which is located at A. So its region of converge lies between the inside the unit circle. So it will converge. Now, with the help of ROC, we will discuss the stability and the ROC by taking the different examples. Here we have find the ROC region for different values of A. So here we have taken the value of A greater than 1, it is 1, and it is less than 1. So it is greater than 1, it is 1, and it is the exponential decaying pulse. This is your rising pulse. And for the different values of A, we have plot the different ROC for the given signals. Now, if the ROC is outside the unit circle, then the signal is unstable. So the main condition or main existence of the ROC is that it should be outside the, if ROC is outside the circle, means this ROC is outside the unit circle, then the system will be unstable. And if its ROC lies inside the unit circle, then the system is stable. Now we have considered the example. Here we have taken the values of A negative. So A value is minus 1.5. This is the region where A minus 1 and A is minus 0.9. And we have taken the ROC for the different conditions, and we've concluded that the ROC is outside the unit circle, the signal is always unstable. And if the ROC includes the unit circle, then the signal is stable. Now we have considered more example. Then we have shifted the unit step function, and it is multiplied by the exponential pulse, and we have find the Z transform. So Z transform is summation of n minus infinity to plus infinity xn z to the power of minus n, and instead of xn we have put the given signal, and we will find its ROC. Now, by putting and solving the above equation and with the summation of the infinite series, xz comes to be z upon z minus a, which means that there will be a zero on the origin and there will be a pole at located at z is equals to a. Now it is inside the unit circle. Now for the same signal, sometimes the two signals are same, but the ROC differentiate the two signals. Now in this case, again we will take the values of a with the different values like this: a more than 1, it is 1, and less than 1. So when we find the different ROC for this conditions, then if ROC includes the unit circle, then the signal is stable, and if it includes the unit circle, then the signal is unstable. So in this case, for the different values of a, we can conclude the different ROC for the given same signal. Now the properties of the ROC. Now we conclude these some properties which we have discussed and we have seen through the different numericals. So the ROC means the region of converge. So the ROC, it is an angular ring in the Z plane centered about the origin, which is equivalent to a vertical strip in the S plane. The ROC does not contain any poles similar to the Laplace transform. Now, if xn is of finite duration, then the ROC is the entire Z plane except possibly by Z is equals to 0 or Z is equals to infinity. So now these are the different discrete time signals and their transform, and which will show the different ROC like this. For xn, it is del n, means it's the impulse whose transform will be 1, and ROC will be the entire Z plane. Now in the second example, what we have done, we have shifted the impulse on the left hand side and its transform is Z to the power of minus 1. So its ROC will not be 0 and all other places. Now we have taken the third example. Here we have shifted the impulse on the right hand side. So its transform will be Z and its ROC will all the places except the Z is equals to infinite. So here we have also discussed the same with the help of continuous time signals and its comparing with the Laplace transform. Now, if xn is a right-sided sequence, then mod of z is equal to r naught. It is in the ROC. Then all finite values of z for which mod of z should be greater than r naught are also in the ROC. Now, if xn is a left-sided sequence, then its ROC will be this is the left-hand side signal. Then its ROC will be the entire plane except at z is equals to 0. If xn is a two-sided sequence, means it contains all the signals that is from minus infinity, 0 and infinity. Then z will be r naught is in the ROC, then the ROC consists a ring in the z plane including the r naught. So it will form a ring whose radius will be r naught. For example, we have seen that xn is equals to b to the power of mod of n, where b is greater than 0, and it is xn we have taken. Now what we have taken the mod of n, so we will consider both the sides of the signal. So b n un and plus b to the power of minus n u minus n. So we have find the ROC of the independent signals, and we have drawn it's the ROC on the Z transform. Now we'll discuss some properties of the Z transform, like linearity. We know that linearity follows the superposition theorem, which means that if more than one signal acting on a system, then the total response of the system is the individual sum of their transforms. So this property shows that this is a one signal, this is two signal, it is multiplied by a coefficient A, and this is multiplied by coefficient B. Then it results that x1n, its Z transform will be x1z, and for x2n, its Z transform will be x2z multiplying by the coefficients. Now in this, we have proved this property by taking the Z transform on the left hand side, and left hand side has been proved with the right hand side. Now time shift. Time shift means if a signal is xn and it is shifted in the time domain by a quantity n naught, then what will be the change in Z transform? So the Z transform will remain the same, only it will be multiplied by Z to the power of minus n naught. Now to prove this, we have taken the Z transform of the left hand side. So by the definition, summation is equals to n is equals to minus infinity to a plus infinity, and this is the signal, and we have find out the Z transform, and by solving it we have proved the left hand side is equals to right hand side. So if it's shifting its minus, then the Z will be multiplied by minus, and if its shifting is n plus, then Z will be multiplied by the plus n. Now, if we multiply any signal by n, so it results in this property, which is known as the differentiation property of the Z transform. And with this, we have find out the taking the Z transform of x, Z is equal to, we know the definition, summation of minus infinity to plus infinity, x and Z to the power of minus n. We have differentiated on both the sides, and by rearranging the order of summation, we conclude that if a signal is multiplied by n in the time domain, then its Z transform will be xz, and which is differentiated in the Z domain, and it is multiplied by minus Z. If we multiply by n square, then this minus Z will be power of 2, and differentiation will be d square xz upon dz square. So what we in this lecture we have introduced, we have discussed the Z transform, and it is given by xz is equals to summation of n minus infinity to plus infinity xn Z to the power of minus n. Then we have discussed the region of converge and its relationship to the existence of discrete time Fourier transform, and what will be the effect of stability. Then we have discussed three properties of the Z transform. One was the linearity, second was the time shift, and third one was the multiplication. Linearity, which follows the superposition theorem. Time shifting means the signal will be shifted either right hand side and left hand side. Then its transform will remain the same, only it will be multiplied by a constant term. And if we multiply by a signal in the time domain by n, then it will result in the differentiation in the Z domain. That's all.